There we go. All right, so we closed it already? Wow. Well, so we've got quite a few things to go over tonight. We got our upcoming event schedule first, our volunteer opportunities, and we got a little presentation from Brad Young, our new observing chairman. Got a little tour of our observatory with the beautiful, beautiful drone footage that was taken last time during our guest night. And then we have news about NASA's latest exoplanet count. And then lastly, we have our presentation from Dr. Robert Zellman. So let's start with upcoming Astronomy Club events. So we've got our next guest and member night, April 23rd. So it's going to be at 7:30. We're finally starting to get back to more reasonable evening hours now. Now, if you have anybody who wants to volunteer or wants to show up as a guest to make sure they RSVP online, if they want to volunteer, check in with either Don or with John Land. Now, our next members night is going to be the following Friday, April 29th at 7:40. So weather permitting, if not, then of course we'll go on normal Saturday. Our next general meeting for the club here is going to be next month, Friday, May 13th at the usual time of 7. This is open to members as well as guests. And then kind of a big deal that's coming up is our next total lunar eclipse. Seems to be getting more and more of those these days. So we have it at Sunday, May 15th through the 16th. Partial is going to start up at 11:28 p.m. Central Time, and then it's going to get interesting about 11:29, 10:28, 11:29. Those are the times. It can't be military time. And it's going to be just a short one for totality, but I don't think we got totality with the last one, so it's going to be a nice little treat for us to see. Now for those, then we've got our next couple of guest and members nights following that in May. May 21st, we have our next guest night, and then members night following that, May 27th, as usual.
All right, if I could jump in real quick here, Brian.
Yeah.
I just want to let you guys know, just in case you have the year schedule, I don't know if they posted your schedule, but the general meeting moved. It was going to be the week before that. So if you now realize May 13th is a new date. John had to move it because I'll be out of town on the weekend before that for a wedding. So that's why we had to move it to May 13th. So maybe this doesn't affect you because you don't know that far out, but if you did know that far out, that is a change. May 13th is a change. Thank you.
Now let's talk a little bit more about this lunar eclipse that's coming up here. So for those of you who have never seen one, there are sort of two different stages of eclipse with the moon. There's penumbra, which is sort of a partial shadow off the Earth, and then there's umbra, which is when the moon falls into the darkest part of the Earth's shadow. Now it's not uncommon for us to get penumbral eclipses. Those are partials, we get those frequently. It's also not uncommon for us to have the moon just sort of skim the umbra and only get a little bit of that totality there. But this is one of the ones where we actually get to see the moon go completely red in the shadow. Now that's going to be a pretty cool event, and this is a lovely little map of the actual one that's going to be happening on May 16th, so this isn't a generic map. Now these things do take a little while to happen, so you're going to need a lot of coffee to stay up for this one, but it is worth it. These are kind of some of the spookiest things you can see in the night sky. So it's going to start up at 10:26 Tulsa time. And, weather permitting, hopefully it's not cloudy. We've had a couple of these nice ones where it's completely clouded over, so Oklahoma weather is as it is, unfortunately. So that's something to look forward to next month. Now let's move on to a little bit more about the club info here. Now we have a wonderful facility out there in that's where we are now, out there in Mounds. And whenever we do these big events, now that we're finally starting to climb out of COVID, we've got a lot of great public interest lately. So we need a little bit more volunteers. So any member can be a volunteer. We ask just for as much help as we can get, especially on those public nights when we are getting bigger and bigger crowds, especially now that it's starting to get less cold. We're going to see a lot more people. So any help, any volunteer, you can be there providing a scope or to help out with scopes that the observatory has. You can help out in the dome with Don. You can help out just guiding people where to park. So any help that you can provide is going to be appreciated. So if you're interested in being a volunteer at any of our observing nights, just reach out to either board member John Bradford or, of course, John Land. And next, I believe, is our presentation from our new observing chairman, Brad Young. So Brad, you out there? Can't see your dark.
I'm Brad Young. I think some of you know me and some of you may not know me. I'm going to be the observing chairman for the club. I'm very happy to do that. Hope I can help everyone in the club enjoy their observing time better. That's my name. Click it, I think it'll go to another, there we go, that's what I do. And here we go. So, as you just mentioned, we have this rural observing site in Mount Oklahoma. It's not the darkest site in the world, but it's pretty close. It's kind of a nice mix of being close enough that you don't have to drive all night to get to it, and at the same time, it is pretty dark. You're going to usually find on public or member nights, or sometimes even on other nights when there's something special going on, you're probably going to find several seasoned and helpful observers out there. There's a pretty core group of hardcore observers that are there a lot, especially on clear weekend nights. And you can go around and talk to them about how they do their observing, what they're looking at, and that sort of thing. Look through the telescope, get some ideas of what you might want to look at or what kind of equipment you might want to get. And what I'd like to do is have sessions, and that can either be here, it can be at the observatory, or it can even be a Zoom meeting, whatever works for everybody. I'd like some ideas about how that might look, and then also what the subject matter would be. I'm familiar with a few of you and where you are as far as your observing goes, but I don't know everybody, and I know that everybody has their own interests, their own level of experience, and that sort of thing. So I'd like to start having some, just not necessarily training sessions, but more of a conversation at the telescope or at the binoculars or whatever we need to do. If anybody's interested in that, you'll see, I'm not sure my email's on here, but I can certainly get that to you. That's my website. You can always leave me a note there. If we go back to the slide, yeah. I'm also interested in doing astronomical observing programs. I don't know if any of you have done any of those or are doing any of those, but I started doing those in about 2000, and they've really helped me gear my observing towards other things. I kind of got into a rut of looking at the Andromeda galaxy every time, and looking at the same things over and over again. I kind of wanted to expand what I was doing, and that's a good way to do that. You don't necessarily have to do the program to get the pin and the certificate. You just do it for yourself, and in any case, you can do it at your own pace. And I think that would be helpful for you. And if you have any questions about that, I'd be happy to answer those. We also have a selection of telescopes on site, a pair of big binoculars at the observatory on mounds. As far as I know, those are open to use. You can't take them home with you, as far as I know, but while you're there at the observatory, you can certainly use them, and you can find somebody to help you set it up, tell you what it's all about, and how to use it. And most of all, what I'd like to say is just ask. If you have a question, if you have an idea for one of these sessions, or if you have any other ideas of how we can work together to expand our observing expertise and enjoyment, just let me know, and I'll be happy to talk to you about it. Okay. About me, that's my website. I don't know why I didn't put my email on there, but I'm pretty sure you can leave me a message on that. Or I can give you my email later if you want it. I'm pretty much only a visual observer. That's my telescope there, and I've been doing visual observing since I was 14, so 42 years. And I have done some remote imaging for specialized things like tracking satellites and just taking pictures of galaxies to see what they might look like when I go search for them visually. But I would say I'm at the pre-kindergarten level of imaging. There are a lot of people in this club that are much better at imaging than I am. And so if you have some imaging questions, you probably will want to go to somebody else, or I can refer you to them. That doesn't mean you can't ask me about them. I'm just letting you know ahead of time that I'm pretty much a visual observer. And so in the vein of that, if anybody wants to offer to help out with the imaging part of it, and I'd be happy to have you help me, and just let me know. Okay, next slide, please. And the takeaway from this is we can help you with anything. I know that's a pretty big statement, but I think there's enough people in this club with different levels of expertise, with different interests, using different equipment, that no matter what it is, the simplest things or even some of the more advanced subjects, there's going to be somebody in the club that can help you. I will try to be sort of a point source for that. I can probably answer most of your questions about visual astronomy, and then, like I said, I'll have to hand it off to imaging. But if you want to learn about the star charts, how to read them, how the sky works, we can certainly help you with that. If you want to learn about observing without a scope, there's a few members in this club that I've met that don't have a telescope yet, and that's okay. There's still plenty of things you can do, either with your eyes or with just a regular pair of binoculars. I do most of my observing with binoculars, tracking satellites, but there's all kinds of other things you can do with just binoculars. And in some cases, that's the best thing to start with. Better a good pair of binoculars than a cheap telescope. I can certainly help you with using a scope, and I put more imaging in little letters to reinforce the fact that I will be looking for somebody else to help with that. As far as the observing programs, we have several master observers in the club. There's lots of people that have done some of the programs, and so there's plenty of expertise there if you have any questions. Another thing is just improving your nights. There's a lot of techniques. We were actually talking, Don Bradford and I were, and Jerry Cassidy and I were talking about techniques before the meeting tonight of how we can improve what we can see, how we see it, make it better. And there's a lot of techniques to using a telescope or just dark adaptation, how you approach the night, how you plan it out, and that sort of thing that I'd like to help you with if you'd like that. And again, anything else about observing, just ask, especially for these sessions. If there's interest in doing sessions, I'd like to do that. I think that'd be a good way to address a lot of questions at once and help as many people as we can, in a short amount of time. And I think that's it. Does anybody have any questions right now or any comments? Or on I guess it's a Zoom meeting, anybody out there? Okay, thanks.
Alrighty, so now we're gonna watch a little video about, you may have heard in the news just a couple of weeks ago, NASA has confirmed that we now have over 5,000 confirmed exoplanets out there. So considering that in the 1990s we had 1, so we've come a long way. So this is a neat little video to celebrate that fact. And there you have it. So 5,000 planets. Just let that sink in for a bit. And once the James Webb Telescope gets to work in a couple of months, we'll actually
start selling online
to start seeing inside of the atmospheres. I hate ads. Well, now we're going to move on to our guest speaker tonight. This is Dr. Robert Zellum. He's an exoplanet astronomer at JPL, and he has been working on ground and space-based observations of the atmospheres of exoplanets, which are, of course, as we just pointed out, planets beyond the solar system. He leads Exoplanet Watch, a really cool citizen science program that helps us to characterize these things. So let's switch over to that video and hear what he has to say.
Again, I want to say welcome to the October webinar of the NASA Night Sky Network. This month we welcome Dr. Robert Zellum to our webinar. Rob is a scientist at NASA's Jet Propulsion Laboratory working on ground and space-based observations of the atmospheres of exoplanets, planets outside of our solar system. I think that's really exciting that we can actually see, and examine the atmospheres of these distant planets. He's observed and worked at major observatories and is involved with developing simulations to predict the ability of NASA and ESA exoplanet dedicated missions to measure these exoplanet atmospheres. Rob is also active in leading citizen science projects to help aid in the characterization of exoplanets. And so later on, he'll tell us a little bit about how you can get involved with helping with this effort. So please welcome Dr. Robert Zellum.
Everyone, thank you so much for having me, and thank you, Frank, for that awesome intro and making me sound a lot smarter than I actually am. I really appreciate that. All right, so my name is Rob, as you said, and today I'll be talking about exoplanets and ultimately finding life in the galaxy. I'm a giant nerd. I love space, and I want to find aliens because I love Star Wars, and I want to ride the Millennium Falcon. But in order to do so, I have to find, or scientists have to find, potential places where the Falcon can be docked. So as we said in my intro, I work at NASA's Jet Propulsion Laboratory operated by the California Institute of Technology. A building, which I haven't been in about a few years, is actually right down here. And this photo was clearly taken thousands of years ago when LA actually had water and snow in it. As I mentioned before, I've always loved space and astronomy. This is actually little Rob at the Kennedy Space Center meeting this year as an astronaut. Sometimes people ask me if I'd ever wanted to be an astronaut growing up as a kid, and my answer is a very firm and hard no. I am deathly afraid of heights. So that's kind of a job requirement, is to not be afraid of heights to be an astronaut. So I do what I think is the next best thing, and I'm an exoplanet astronomer. So what does this mean? Let's quickly unpack this. Well, exoplanet, that's just simply short for extrasolar planet. Extrasolar means anything beyond the solar system, outside of the solar system. Where planet, obviously, equals planet. So if we cram them together, exoplanet is any planet outside of our own solar system. And I'm an astronomer. If you don't know what that is, you're probably in the wrong talk, but as you are all aware, that's someone who stares at the sky, or more likely, in my case, their computer for way too long. And I work at NASA's Jet Propulsion Laboratory working on exoplanets, trying to characterize them to figure out what contents are in their atmosphere, working on missions, instruments, both on ground and in space. And ultimately, I'm working towards helping answer that question. The ultimate question is, are we all alone in the universe? Or is there life elsewhere out there? So I should say really quickly, I am married to a historian, and if I do not show this next slide, she'll bust into this room and kick me off of Zoom. So it's always also helpful to look back from where we came to see where we're going. So even though exoplanet science is one of the newest fields in astronomy, it's only about 20 to 30 years old, depending on how you count. The idea about exoplanets, about planets outside of our galaxy, our own solar system, is not a new idea. This has been around for hundreds of years. So for example, Giordano Bruno, that 16th century philosopher who looks a lot like Emperor Palpatine up there on the right, actually postulated the existence of exoplanets. And Isaac Newton, as you are all aware, he invented the fig Newtons. He said in his work on Principia, where he discussed the theory of gravity, he also said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, we have 8 planets in our solar system, 8 because Pluto's not a planet. We have 8 planets in our solar system orbiting around the sun. And it stands to reason that when we go out into the night sky and we look at all those points in the sky, all those stars, that they have planets orbiting around them as well. And we know that these 2 dead dudes are absolutely correct now, hundreds of years later. As our technology got better, as we learned how to look, where to look, when to look, we have started discovering exoplanets and at an ever-increasing rate as well. So we now know that planets are ubiquitous, they're everywhere. And thanks to some NASA missions, we now know that there are at least as many planets as there are stars in the sky. So this is all well and good. We're discovering tons of exoplanets. We've actually discovered over 4,000 as of today. But we want to find life, right? We want to find aliens and determine if, human life or life on the Earth is something common or if it's something unique. And to do that, we sort of have this sort of 3-step method that I wrote down here. First, you have to find the exoplanet. Then you can determine if it can support life. Then you actually have to find the life itself. So let's look at the first step. How do we find exoplanets? Well, there's actually a problem. It's really difficult to see exoplanets. They're so very far away. We typically only see the star that's orbiting because the star is so much brighter than the planet. The planet is so much dimmer. So we either need to block out the star to block out its light and see the small planet orbiting around it, or we need to use other methods to infer that the planet is there. So there's actually a variety of methods that we use to find exoplanets. The 3 I'll be focusing on tonight are radio velocity, transit, and direct imaging. These are arguably 3 of the methods that have given us the most information about exoplanets, at least the radio velocity and transit methods. And then I work personally also on direct imaging methods. So I have to, I'm contractually obligated to say that or my funders will get mad. So let's look first at the radial velocity method. Well, the radial velocity method is sometimes called the Doppler shift or wobble method. When you have a planet orbiting around the star will gravitationally tug on the planet and cause the planet to orbit it. But the planet also exerts its own gravity on the star. And if the planet is big enough or close enough, it'll cause the star to wobble back and forth. As the star wobbles towards us, its light gets blue shifted, its light gets compressed. It's a lot like Doppler shifting. It is Doppler shifting. So if you're ever walking down the street and an ambulance or a very loud car passes you, these sound waves are actually compressed, which increases the pitch and the frequency of that sound. Same thing happens with light. As that light comes towards us, the wavefronts are compressed and the light is shifted towards bluer wavelengths. Then when the star goes away from us, those light waves are stretched out effectively. The waves are increased and the light is shifted towards red wavelengths. And this gives us the mass of the planet. The bigger the planet orbiting around the star, the more gravity, the more it tugs and wobbles its star back and forth. The other method that we can use is called the transit method. The transit method is when you're detecting when a planet passes in front of a star. So we're observing these host stars. We might get lucky and a planet might occasionally pass in front of its star, block out the star's light, and effectively cast a shadow all the way back on the Earth. And transits are extremely helpful and important because they allow us to directly measure how big that planet is relative to its host star. The bigger the planet, the more light it blocks out, the bigger the dip in brightness of the host star. But at best, this dip in brightness is typically on the order of about 1%. This method, as I'll talk about later, also allows us to study the atmospheres of these planets by observing how the planet's atmosphere blocks out and absorbs light from its host star. And this method has been used very successfully. It's been used to discover about 3,000 of the 4,000 currently known exoplanets. So transits, it's actually relatively cheap to observe them. As I'll talk a little bit later, you can use telescopes as small as like something that's 4 or 6 inches. I've also saw posts occasionally online a few years ago where someone used a single DSLR camera on a barn door tractor to observe a transiting exoplanet. So no telescope at all. Again, it gives you the planet's size, There are disadvantages though. You're biased towards large planets in short period orbits. You're biased towards planets that are larger, that block out more light, and therefore have a larger signal. But there's also false detections as well. And you have to have that geometry, just like radial velocity. The planet has to be orbiting in this plane, so it blocks out the star relative to your line of sight. If it's orbiting perpendicularly, you won't see any transit, and you won't see any planet detection at all. So I mentioned before that the transit method has been used successfully to discover about 3,000 of the 4,000 known exoplanets. And that's thanks to ground-based surveys and space-based surveys, one of which was NASA's Kepler mission, discovered a few thousand. And now there's a mission that was launched just a few years ago called NASA's TESS mission. TESS is doing a full sky survey over the next few years. And TESS is predicted to discover potentially up to 10,000 new exoplanets. So today we know of 4. TESS might discover an additional 10. And the reason that it's important to discover new planets is because the transit method is used repeatedly and routinely by space telescopes and ground-based telescopes, one of which is the Hubble Space Telescope, which has looked at tens of planets. James Webb, when that launches, hopefully in December, that will be observing hopefully tens to hundreds of planets. Ariel, a European Space Agency mission that'll be launching in the next decade, is dedicated to exoplanet science and will be observing hundreds to 1,000 planets. And then Astro 2020, these are the next flagship missions that NASA is considering right now, that we'll actually potentially be hearing about as soon as next week or the week after. Those spacecraft are likely going to be using the transit method as well to actually search for signs of life. So we've been routinely using the transit method to look at and characterize the atmospheres of these planets. And it's likely that we will continue to do so for at least the foreseeable future. But in order to observe a transit with these space telescopes or even any ground-based observatory, we have to know very precisely when that transit will occur. So let's pretend I write a Hubble proposal to observe an exoplanet. And I look up online and I determine that planet will be observing or transiting its host star, and I estimate that it will transit its host star in this red dashed line. But let's say that that planet has some uncertainty with regards to its timing. That planet could actually transit its star a little bit earlier than I anticipate. And there's 2 ways to get around this. One is by building additional buffer to our observing campaign to ensure that we don't miss the transit. But that's not really using this time very efficiently on that telescope. You know, if I could build in an extra 10 or 15 minutes to my Hubble proposal or my James Webb proposal, while it doesn't sound like a lot of time, if you do the math, it's really costly. And that's also additional science that you could have been doing on other cool science cases as well. So there's really this need on some of these targets to update their mid-transit times, to update their parameters, so you can more accurately predict when the next transit will occur, and you can use these very, very precious resources a lot more efficiently. So that got us thinking, well, why don't we use small telescopes to do this? We're working a lot with a group called the Micro Observatory out at Harvard CFA, and they are routinely getting data from the robotic 6-inch telescopes both in Tucson and in Massachusetts to observe transiting exoplanets. And we were just quite honestly blown away by the data quality. These are 6-inch telescopes, they're robotic, their pointing is not perfect, the target slews by hundreds of pixels across the frame, it observes any given night. This is an example of transit light curve I'm showing on the right. It's actually a relatively dim star about 11th magnitude. And despite all those issues and those confounding variables, we're actually able to get a really, really nice looking and science grade light curve. And I can say it's science grade because we actually published this in PASC in 2020. So that got us thinking is that if a single 6-inch telescope could really make these high precision measurements, what does that mean about other folks out there that have their own telescopes that can actually really contribute to NASA science and goals in a very meaningful way? So that led us to launch a project called Exoplanet Watch, which is where citizen scientists monitor transiting exoplanets. So Exoplanet Watch is a campaign aimed at these citizen scientists who routinely observe some high priority targets. This is a collaborative effort to complement existing surveys. So for example, there's basically a European version of us called ExoClock that's been set up to help the aerial mission, and in collaboration with them. All of our data will be immediately public to the entire community. There's no embargo phase. So as soon as the data is processed on our end, we immediately push that up to our website. There's an opportunity for community feedback and target requests. We're actually getting requests by professional astronomers right now, even though we have yet to officially launch to professional astronomers. We actually have 2 observing campaigns coming up, one in November and also one in December. And the one in December is actually to directly help out a James Webb proposal observing run that will be happening the next year. So if you're interested in actually directly helping out NASA missions and goals, you can help us observe these targets and use these resources a lot more efficiently. What I'm really excited about as well is that we're requiring observers to be listed as co-authors on any published results. If you do the work, you deserve the credit. I just want to give a big shout out to NASA's Universal Learning that's funding this entire process. Universal Learning is this really great organization that's funded through NASA that does various public outreach events and products as well, from videos to talks like this. So our goals for Exoplanet Watch, we have an educational goal to engage the public in exoplanet citizen science, increase their confidence about the ability to do science. And then we also have, those boring old typical science goals, like, efficiently using NASA resources so Rob doesn't get yelled at by NASA and fired from his job that he loves. So those are all good things to do. So I'll quickly just go through the user experience. First, you plan your observations. We advertise on our website priority targets for each US time zone, since we are a US funded endeavor. But you can use whatever transiting planning tool you want, such as the Swappmore Transit Finder or the NASA Exoplanet Archive. Ultimately, you can observe any transiting planet you want. It doesn't matter. We'll take any data you can get, even if it's not one of our priority targets. You then observe your own transits with your own equipment. So you go out in your backyard or you dial up your robotic telescope and you do your own observations. We're also working towards, by the end of next calendar year, opening up even further so that users who do not have access to their own telescopes, who don't live in dark sky conditions or even clear sky locations, can actually get some data that we'll procure through robotic telescopes, such as the Micro Observatory. And we'll be launching that by the end of next calendar year. We then reduce or analyze your own observations. We have our own data reduction tool called Exotic that I'll be talking about a little bit later. You can use whatever you want. I know a lot of folks really love Astro Image J. You can use that for sure. You can also use any sort of homegrown data reduction tool, as long as the file is in the correct format for uploading to the American Association of Variable Star Research Observers website. That's all that matters at the end of the day. We're really grateful for our partnership with the AAVSO. They have their own exoplanet data database they're letting us use and our users use for free. And it's been a really great process so far. Then once you upload your data, you just sort of sit back and relax and hopefully get published as a co-author. Alternatively, you can use any of our data products on our website that are immediately and publicly available to write your own research papers as well. The only thing we ask in return is if you use someone's data and it hasn't been published before, you ask them to be a co-author on your paper, or at least you offer them to be, and then you include some acknowledgement and cite one of our papers as well. Very easy peasy. Then on the back end, here at JPL, we have these 2 servers that routinely scrape the AAVSO pipeline database. And it does this right now about twice a week. We're gearing up for nightly scrapes. Then we reprocess the data. This is to make sure that if any of the values get updated, we can have the latest measurements on our end as well. And then we immediately publish them to our website. We have no proprietary phase. So I mentioned Exotic. This is our exoplanet transit interpretation code. This is a complete analysis software that can run on your own computer. It runs on Windows, Macs, and Linux boxes, so basically anything. And it has a really nice GUI, and it can take your raw image files, your raw FITS files, and it can fully analyze, extract the flux, do the calibrations, do the model fitting as well in as little as about 5 minutes. As far as I'm aware, this is the fastest data reduction tool on the market, and it's free. And it also does these really nice light curve fits that are fully statistical model fits that we actually use to publish. Another cool feature about Exotic is it produces these real-time light curves. This is actually based upon some code that we use at Palomar Observatory, for example, that shows you the transit happening in real time. We use it because we want to make sure we're observing the right part of the sky and not wasting Palomar time. But also, if you wanted to, when we can have star parties again, hopefully soon, you can also use exotic to show a transit-like curve in real time. When you're observing a transit, they're kind of boring. And if they're boring, that's great, and there's nothing bad is happening. You're observing a star, you're trying to watch this star dim by 1% over a few hours. And that's kind of hard to see by eye, it's just like a static field. But if you have this real-time plotter set up of exotic, you can point to your monitor while people are going by at star parties and say, hey, look, we're actually observing this exoplanet hundreds of light years away right now, and it's casting a little shadow on the Earth. So that's Exoplanet Watch. We actually launched about 3 months ago to amateur astronomers, sorry for the typo, and we're now launching soon, hopefully within the next 2 to 3 weeks, to professional astronomers. You can contact us by emailing us at exoplanetwatch@jfield@nasa.gov. You can also visit our website down there below, or simply just Google NASA Exoplanet Watch, and hopefully we're one of the top results. All right, I'll get off my soapbox there and get back to the science. So I was talking about how we find exoplanets. So we have the rate of velocity method, which is the mass of the planet. We also have the transit method. This is the size of the planet. There's also this third method called direct imaging method. And as you've probably figured out by its name, direct imaging purely means taking photographs of exoplanets. However, as I alluded to earlier, this is really difficult, and there's a really big problem with this, is that the planet's light that it absorbs, or that it reflects or emits, is really dwarfed by its host star. So let's take a thought experiment. Let's take a large planet, like a Jupiter-sized planet. Let's also get this planet when it was recently formed. So it still has a lot of heat left over from its formation, so it's big and bright and emitting a lot of light. You take that Jupiter-sized planet and put it around a sun-like star. That's like looking for the light of a firefly flying around a lighthouse, and you're observing it from the other side of the country. Because that planet is 1,000,000 times fainter than its star. Now, what about for an Earth-sized planet, an Earth-like planet? That's the ultimate goal here, is to start characterizing and finding planets that could have life on their surface. Well, that planet is going to be 10 billion times fainter than its own star. That's like looking for one bioluminescent alga around that same lighthouse. So how do you block out the star without blocking out the planet? And how do you block out the stars so you can see the planet's light at all? Well, that's where direct imaging comes into play. Direct imaging is literally blocking out that light of that host star using something called a coronagraph. Block out the light from the star and allows you to resolve the light from the planet next to it. It's a lot like during that solar eclipse that we had a few years ago, where instead of the moon passing in front of the sun, allowing you to see the corona of the stars around the sun, you actually use a piece of hardware called a coronagraph to block out the star's light and allows you to resolve the planet's light as well. So I have this handy video to help describe this method. I'm going to check my audio settings. Okay, I should be good to go. And I can take a sip of water, break too.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. W-FIRST doesn't block the star's light with an opaque disk as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear, while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects the distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, W1st will provide the first look at individual planets in star systems that might be similar to our own.
So we'll be coming back to W1st, now called the Nancy Grace Roman Space Telescope, in a few moments. But hopefully everyone got how chronographs work in space and how they work at all. There'll be a pop quiz on this later, so the answer though is magic. It all works by magic. In all seriousness, it's a combination of hardware that is able to block out the light from the host star, as well as any internal aberrations or internal reflections in the instrument itself. And then there's also really cool post-processing techniques, software techniques that people use to further increase the fidelity of the data. So direct imaging has been used very successfully for many years, including on the ground here on the Earth. There's actually some exact direct imaging data taken from, I believe, one of the Gemini telescopes by Jason Wong. Here at the center is actually the black chronograph that has blocked out the light of the central star. And each of these 4 points of light right here are actually 4 little exoplanets. And as you can see, they're orbiting around this star. So this data was taken over about 7 years. So we're actually looking at an extrasolar solar system orbiting around its host star in real time. And this is just mind-blowing to me. We're able to observe these planets orbiting around this star. Okay, so now what? Well, we have discovered over 4,000 exoplanets, but that's all well and good. We can detect planets, who cares, you know. What we really want to do is we want to take that next step. How do we make the leap from, or the next step from planet detection to now planet characterization? We want to know what these planets are made out of. Are they water worlds? Are they gas giants? Are they terrestrial planets that could have an atmosphere that could support life? But to answer that question first, we have to figure out, does the planet even have an atmosphere? And if so, if it does have an atmosphere, what molecules are present in that atmosphere? And if it has molecules in its atmosphere, could it actually support life? If so, then does it have life? So this takes us to our next step, is we have to determine if a planet can support life. So one of the metrics that's usually used to talk about this is the habitable zone, also called the Goldilocks zone. And this is the zone in the orbit of a planet where liquid water can survive on a planet's surface. It's basically the distance between the planet and the star. The planet's not too close, it's not too hot where water boils off, it's not too far away, it's not too cold where water freezes out. It's at a temperate location, it's where the temperature of these planets is just right for liquid water to survive on the surface. And this is very important because life as we know it requires liquid water to survive. So if we take a top-down view of our own solar system with the sun, Mercury and Venus are a little bit too close, a little bit too hot. Mars is a little bit too far away, a little bit too cold. But the Earth is in that Goldilocks zone. It's not too hot, it's not too cold, it's just right for water to survive and life to survive on its surface. So that gives us sort of a range that we can bet on basically, you know, should we look at planet A or planet B? We can sort of use this definition of a habitable zone to whittle down our planet list to prioritize what targets we want to look at. But ultimately, what we want to do is we want to determine what molecules are in the planet's atmospheres. Does it have water, methane, carbon dioxide, carbon monoxide? Well, to do that, we actually use something called, believe it or not, Beer's Law. So let's look quickly into Beer's Law. I have a nice little definition that describes and explains it here. That is, studying for a test or doing homework while beer is involved, making difficult classes such as physical chemistry more bearable. That's a great definition. It's actually the definition I routinely use as a graduate student at the University of Arizona to help me get through classes. But the one I'm actually more so thinking about is this. Beer's Law describes how light is affected, how it's absorbed and scattered in and out of the beam. So let's take a chamber of gas and let's fill it full of like carbon dioxide or water or something like that. We put a light bulb behind that chamber of gas and we look at it on the other side. We expect that light to be a little bit dimmer. And that's because the light from the light bulb is being absorbed by that chamber of gas. You can actually mathematically describe it to this equation right here. So Beer's Law allows us, by looking at what the light should be and observing how it actually is, we can actually back out the composition of this gas that's being absorbed in the middle. So we can actually use light to figure out what molecules are present in many astrophysical sources. So for example, let's say we're an astronomer using a telescope, observing a yellow star. Well, the yellow star will emit yellow light, and then we'll observe it and it'll look yellow. Makes sense. But what happens if we put like a cloud of gas and dust between us and the star, like a nebula? Well, that big cloud of gas and dust will absorb that yellow light and actually cause it to slightly redden a little bit. So if we use Beer's law, we can observe what a planet or not. So if we observe what an object does look like, in the case the star looks red, and we compare it to what it should look like, yellow, we can then use Beer's law to determine the composition of the absorber. We can then figure out, for example, that this cloud actually has molecules in it. We can also apply this to exoplanets. So an exoplanet, a lot of them, just like the Earth, has a hot core. That hot core actually emits light. And if we use a gaseous planet, like a Jupiter-sized planet, or a Jupiter-like planet, that warm core will emit light that then is escaping through its atmosphere. And the atmospheric layers are slightly cooler than its inner one. And that causes that light to go from yellow to red. So then astronomers at the other end of our telescopes can then say, hey, that planet has methane on it, just by directly adapting Beer's law to those measurements. Similarly, we can look at something like a Jupiter planet and look at how light is reflected off its surface. So in our own solar system, Jupiter takes the light from that yellow sun, and then it reflects it back to us slightly reddened. We can then, astronomers on the other end, can use Beer's law to figure out that that planet has clouds on its surface. So again, Beer's law allows us to characterize an exoplanet's composition by observing how it emits, absorbs, and reflects light. So literally, just by looking at light, we can figure out what things are made of hundreds of light years away. So here's some actual data for some exoplanets. On this axis is about 7 last time I counted. 2 days to count again, exoplanets. On this axis, we've arranged them, and by me I mean Julien Rameau, the GPI team, has labeled them in terms of hot on the top and relatively cool on the bottom. On the x-axis here are a variety of wavelengths. So what they've done is they've observed these exoplanets at multiple wavelengths of light. And what they're able to do is basically match this up with where other molecules are routinely predicted to absorb light. So water, for example, absorbs most strongly at these wavelengths. So if you see a bump or wiggle at these wavelengths, the planet likely has water on its surface. These wavelengths correspond to methane. This wavelength passband out here corresponds to carbon monoxide. So just by looking at these spectra, how the light varies with wavelength, you can actually figure out the composition of these planets. So some of you eagle-eye observers out there might have noticed these gaps in the data. Well, this data was actually taken from the ground, the surface of the Earth. And these passbands right here, these red zones, are actually where the Earth gets in the way. Where stupid things like water actually absorb so much light we can't see through those passbands. So if you can't observe them on the ground, what do? Well, you go into space. This is why space observatories are so important. It allows us to observe outside the Earth's atmosphere and to see at wavelengths that are normally obscured partially or even fully by the Earth's atmosphere. So one mission that you probably all heard about is the Hubble Space Telescope. Hubble actually has been observing water absorption. And it's observed that about 50 exoplanets, I believe, or so. And it's able to access that passband because it's able to fly outside the Earth's atmosphere and actually look for water. So in other words, the Earth's atmosphere can actually prevent us from observing and monitoring molecules that we want to see because those very same molecules get in the way of the Earth's atmosphere. And that's one of the reasons we're so very excited about the launch of James Webb. This James Webb is the successor to the Hubble Space Telescope. It also expands upon the Hubble Space Telescope's wavelength coverage. And in addition, it's just purely a giant telescope, folks. Hubble's about a 2.5 meter telescope. This is about a 6 meter telescope, so about 20 feet across. This purple thing on the bottom is its solar shield. It's the size of a tennis court. This telescope is such a giant beast that they actually have to fold it in on itself like origami to fit inside the rocket nose cone fairing so it can be launched into space. And then once it gets out into orbit, it actually slowly unfolds for many, many days to get its full size. I was actually very lucky enough to see this when I was out here in LA for testing as well. And this sort of our reason for why we're so excited about space-based telescopes is why we're also very excited about the upcoming launch within the next 5 years, likely 2026, that date, sorry, of the Roman Space Telescope. So the Nancy Grace Roman Space Telescope was named after Nancy Grace Roman. She was the mother of the Hubble Space Telescope. She's one of the major forces to getting actually Hubble launched by NASA. And this telescope is really cool because it actually has 100 times the field of view. So what Hubble would take 100 observations to make, Roman can do it in one single shot. And one of the instruments that's on board is the chronograph. And that actually does direct imaging of exoplanets. I'm really excited to be working on the Roman chronograph because it really is a stepping stone or a technology demonstration to get us from where we are to where we want to be. Currently, direct imaging is typically done by large ground-based telescopes. And these telescopes are routinely or typically seeing planets that are far from their host star, planets that are very young and therefore still radiating light left over from when they formed. But where we want to be eventually is we want to find Earth-like planets. We want to find planets that are small, that are radiating or reflecting less light, that are cooler, that are also closer to their host star. And Roman allows us to have that stepping stone to get there, because Roman will allow us to observe closer in, cooler planets, also maybe potentially smaller planets, but definitely planets that are true Jupiter analogs, which will be pretty incredible. So actually Jupiter-sized planets and Jupiter-sized orbits at Jupiter temperatures. And that technology and all those lessons learned will be directly applied to future missions that will be observing that holy grail, Earth-sized planets orbiting around sun-like stars. So given all these great things, why would we even bother with the ground? You know, space-based telescopes are not limited by Earth absorption. They're minimally impacted by sunlight, but they're very limited both in available time and wavelength space. Our space-based telescopes are truly a very precious resource that the entire community is scrambling basically to apply for time for. Ground-based telescopes, on the other hand, there's numerous platforms for instrumentation. There's a ton of telescopes across the world. But we do have to deal with things like the Earth's atmosphere. So with that in mind, I'm actually the JPL commissioning lead of a new instrument that's being tested and commissioned right now at Palomar Observatory out here in Southern California called NESI, the New Mexico Exoplanet Spectroscopic Survey Instrument. And there's the 5-meter, 200-inch Hill telescope. It's a very historic telescope that for about 50 years is the world's largest. And you know, this is a telescope that was built before exoplanets were even discovered. And it's pretty cool to be using such a historically significant telescope, and a big telescope as well. And the major difference there is just our instrumentation, and it allows this telescope to see exoplanets. So let's get into a cool photo that I took the other day of Nessie. No, that's a mythical sea creature. Sorry, everyone. This is actually Nessie. That's the blue thing right here on that silver handling cart. You're seeing this hardware. I'm doing some testing, I think, in one of the labs at Palomar Observatory. And there's Nessie actually installed at the top of the telescope. And I can talk about this later if anyone has questions about it. Nessie sits at the top of the Palomar Observatory. It replaces its secondary mirror, giving a nice big field of view. And when we actually did our fit tests, myself, as the commissioning lead, went up there with my boss, Mark, and Mark is smiling at the camera. He's actually laughing at me, guys, because I'm definitely afraid of heights, and I'm about 100 feet up in the air working this instrument, so he's really enjoying my pain, but just took out a really cool photo and kind of a weird selfie out of it as well. But you know, we've been, for the last year or two, been making really nice transit observations of transiting exoplanets, and hopefully very soon we'll be directly contributing to characterizing the atmospheres of these planets. All right, so we've been talking a lot about how to find planets, how we can use Beer's law to look into its atmosphere, to determine the composition of these planets, to see if it has molecules like water, carbon dioxide, methane, things that life needs on the Earth to survive. Now we take the next step. We have to find life on its surface. Just because a planet could support life doesn't guarantee that life exists on the surface. So let's do a thought experiment. How do we find life? What are the things we would look for? Well, let's pretend we launch a satellite into space, and while it's zooming out the outer parts of the solar system, we have it turn back and look at the Earth. We can have it analyze the reflected light from the planet and use Beer's law to look and see if the planet has an atmosphere, if it has oxygen that can be made by algae that makes ozone. We can look for water, or we can look for signs of biological activity like cow farts, right? But we have to rule out all other explanations. We're currently finding water, we're currently finding methane, we're finding a bunch of molecules on these planets. The majority of these planets are large planets that are very, very close to their host stars, called hot Jupiters, and they're mass visible to life. So you really have to rule out all other explanations. Or alternatively, you can just send messages to talk to aliens directly. So Voyager 1 and 2, they were actually built at JPL. They were launched in the mid-70s, and they did this grand tour of the solar system. And they have these golden records on board. And what these have is they're actually recordings of Earth sounds and also a bunch of different languages saying greetings to people. And they also have pictures of Earth as well. And this golden record is so that alien civilization, if they find Voyager 1 and 2, they can then be instructed on how to make the phonograph, how to project the picture correctly on their TV screen, and then where to find us by looking at a bunch of pulsars. It's pretty cool if you ask me. Alternatively, you can also talk to aliens by sending them messages. Back in the day, in the mid-70s as well, we used Arecibo, rest in peace, unfortunately. This was that time the world's largest radio telescope was so big that I was actually nestled in a valley between mountains. And what they did is they beamed this message out to a globular cluster called M13, where they saw tons of stars, so they potentially had tons of planets. And they sent out this message right here on the right. So you can probably figure out the red thing is, that's a person. At the top in white is instructing aliens, hey, we're not too dumb, we know how to count, we know about molecules. This double helix thing, we know about DNA. Here's how we sent our message. We sent to this radio telescope, and here's where we live. So there's the sun, Mercury, Venus, Earth elevated, because that's where it sent the message. Mars, Jupiter, Saturn, Uranus, Neptune. And guys, this was the 70s when they didn't know any better. They have Pluto on here, but we know better today. Pluto is not a planet. So basically it's saying to aliens, hey, we're this intelligent race. Here's where we live. Come and slay us. Hopefully, we'll learn from Independence Day and cryogenically freeze Will Smith. That was Battle of the Alien Onslaught. Alternatively, we can also send messages to aliens. So, for example, back in 2008, there's a social media network called Bebo. It's big in Europe. They actually beamed some messages to the star system called Louisa 581. And planets C and D are potentially in the habitable zone around that star. So, messages will be arriving in just a few years in 2029. And if there are aliens there and they immediately reply, we'll be hearing from them in 2049. So these efforts are still ongoing, which is pretty cool. So the question is, where are we now? So unfortunately, despite what the History Channel and Ancient Aliens might tell you, we have yet to make any conclusive detection of extraterrestrial life. And the question is why? Why haven't we found aliens? Planets are everywhere. There's at least as many planets as there are stars in the sky. Why haven't we found life out there? Well, maybe our technology isn't good enough. It wasn't until the advent of digital cameras in the 90s that we had the technology necessary to actually see the signal of exoplanets. And once we knew how to look, when to look, we could then apply those, and we started finding planets everywhere. Alternatively, maybe we just haven't found them yet. Maybe they've been talking to us on this patch of the sky, and we've only been looking over here. One great analogy that I really love, which is taken from Contact actually, is that if we were to take the known universe and shrink it down into the size of the Earth's oceans, While we think we know a ton about everything, we have yet only really explored the equivalent of a cup of water. So there's still much more out there that we have yet to explore, discover, and understand. Or maybe alternatively, maybe we are all just alone, and maybe life really is that unique and only exists on Earth. But to avoid leaving on a depressing note, today we are actually standing at a really cool time to be part of exoplanet science. And I've actually, over the course of my own career, been able to sort of experience and watch it grow from its very beginnings, from when the first planet was discovered in the mid-90s to today. We have this amazing foundation given to us by ground-based telescopes, by the Hubble Space Telescope. Spitzer's another mission that's been doing excellent exoplanet work before it was retired about a year or two ago. Kepler and TESS are planet hunting missions. The James Webb Space Telescope is the successor to Hubble and will really greatly expand our knowledge about exoplanets. And then the Nancy Grace Roman Space Telescope, the chronograph instrument, will allow us to observe via direct imaging other worlds. And this is all great because these are giving us so much foundational knowledge that we can use for next generation of missions. So right now, astronomers are getting together and are releasing, hopefully in the next week or two, a report about the direction that the field should be going on in the next 10 years. There are 4 flagship missions that have been proposed to this committee. 3 of them are LUVOIR, HABEX, and the Origins Space Telescope, or OST. And these 3 missions have all been explicitly designed to find life or search for life on exoplanets. So, and these are all launching hopefully as soon as the 2030s or 2040s. So perhaps within the next decade or so, we'd be able to finally answer that age-old question of, are we alone in the universe? So with that, thank you so much for your time. I really appreciate it and happy to take any questions.
All right, thank you very much. We've got some good questions going here. If we have any more, please add to this as we go. And let's get started right off. So Darian asked, and he modified his question, but maybe we can make this more general too. He said, originally he said using the transit method, and then he asked, meant radial velocity, but maybe you could deal with both. How accurate is the ability to determine the mass of an exoplanet? Do you know of a good reference or publicly available software that explains the math and physics required to measure the mass of exoplanets?
Yeah, that's a great question. And it honestly depends, unfortunately. So it depends on the brightness of your host star and the size of your planet. The bigger the planet, the bigger the wobble on this host star. So the bigger the signal, the easier it is to see. The brighter the host star, the better your measurement quality will be as well. So there's unfortunately not like there's the exact answer, because it does vary from target to target, from host star to host star and planet to planet. But effectively, at the end of the day, what you're doing is you're measuring that wobble of the star. You can actually, it's almost as simple as fitting sine waves to that signal. And the amplitude of that sine wave gives you constraints on the mass of the planet. And then the periodicity, the frequency of that sine wave tells you how quickly that planet orbits around that star. So as far as references, there's a ton. What I recommend you do, though, is you go online and you Google NASA 5 ways to find an exoplanet, or 5 ways to discover an exoplanet. They actually have some really nice hands-on animations and descriptions on how this actually works. So that's a great resource as well.
All right. There was a little bit of a discussion in the chat having to do with cameras. And so Gregory posed the question, what type of camera is required? He was thinking, and I'm not sure what the acronym, ZWO, ATIC, etc. And then there were some questions about the chips as well.
Yeah, doesn't matter. Anything, as long as it collects the photons, that's all we care about at the end of the day. We're actually experimenting with some ZWO cameras right now. Also, I know Unistellar, for example, is using ZWO cameras, I believe, in their chipsets on their EVscope, or yes, EVscope. And basically, at the end of the day, they just care about measuring the light and collecting the photons. You could use a DSLR camera. You have to do some detrending of your array because of the Bayer array. We have people using CMOS cameras, CCDs. So really, it's anything and everything, honestly.
Are there any resources that people maybe could access so that they, or maybe that's on your exoplanet website, about recommendations and settings and things like that.
Yeah, we're actually developing that right now, and it should be up on our website hopefully in the next week or two. We do have other resources with links elsewhere. For example, Dennis Conti of the AAVSO has a really nice sort of how-to guide, and there's tons of YouTube videos. But alternatively, you are more than welcome to sign up for our project, join our Slack channel. It's how we all interact and communicate with each other. We have a ton of amateur astronomers on there that are really knowledgeable, and a lot more knowledgeable than I am, and they can definitely recommend some different setups for various budgets as well. Oh, and thank you for the correction, Phil. Appreciate it.
Hey, Randall asked a question. When you talked about Beer's law, you started by stating, if we know what the light from the star should look like, how do you know that?
Yeah, that's a great question. This was always something that would confuse me as an undergrad all the time, is how do you know what it looks like or should look like if you're looking at it, what it does look like. So you can actually sort of figure out by looking at a star, you can say, oh, that star is like a G-type star, but we're noticing that these wavelengths are blocked out, or that the light is just shifted red or blue. So basically you have to look at the entire picture to figure out what the star should be looking like. And then that way you can sort of infer what sort of information is missing. Like for Beer's law, if you're observing a G-type star, like a sun-like star, that should be emitting yellow light. You put that gas cloud in front, that gas cloud is actually going to block out or absorb light in various wavelengths according to the molecules that are in the gas cloud. So you can basically see these, you can see the spectrum of the star, and you'll see these little lines that dip down that are indicating absorption by that gas cloud. And you can actually look up that pattern and then figure out what molecules are doing the absorbing.
Right, so Marco's asked a question, fairly specific here. Any news about the TRAPPIST system? A few years ago, there was a lot of noise and it was in the news a lot.
Yeah, so the TRAPPIST system, I actually have a little quick slide about that. 1 second. Find that in my giant slide deck. Right here, I'll share my screen. So the TRAPPIST system is very exciting because it's a multi-planet system. It has 7 planets that are all roughly Earth-sized planets orbiting around a small star. And these are all Earth-sized, but planets E, F, and G actually might be in the habitable zone of their host star. So these 3 planets actually might have conditions conducive to life. These planets have actually been observed by the Hubble Space Telescope, and Hubble has found evidence of water potentially in the atmosphere of all 3 of these planets. And as far as I'm aware, James Webb will be observing the system as well. I believe that's still the case. So stay tuned. Once James Webb launches in December, it goes through a bunch of commissioning over the next few months. Perhaps within the next year, you might, or 2, you might hear about new observations with this new observatory of the TRAPPIST-1 system.
All right, and I think you just answered Scott's question. He says, when will JWST come online? So maybe a year from now.
Launches in December, and then I forget the exact timeline, but it has a bunch of commissioning steps. So it takes time to get out from the Earth out to its final orbit, and then it takes time to unfurl. We have to check all the instruments, make sure everything survived, everything's operating correctly and sufficiently, and then it can start doing those observations. I believe observations are slated for next fall for the science program, and observations will likely be happening before that for commissioning the instrument to make sure things are working correctly.
All right. Okay, we got a couple more questions here. So Stephen asked, how well does the radio velocity detection method work for orbits of planets that are perpendicular to our line of sight?
And you're absolutely right, Stephen, it doesn't work at all. So if the planet is orbiting perpendicular to our line of sight, the star will be moving up-down direction, and we won't see the Doppler shift of that light. So the radial velocity method and the transit method both rely upon that geometry. The planet has to be orbiting within that plane that is parallel to our line of sight, so you can either see the planet block out the light of the host star, or we can see the wobble of the star as the planet tugs on its host star. So you're absolutely right. We're missing, or we're not able to detect some planets because their orbits are perpendicular to our line of sight, and they don't cause either a transit or a radial velocity wiggle.
Okay, we've got, I think we've got time for just a couple more questions here. And these are a little more philosophical. I like this one. Mustafa asked, finding life in faraway places means that the life on Earth will not be simultaneously contemporary. What we find will really be from the distant past, right?
Potentially, I don't know. That's a great question. Whenever we look in space, the farther away we look, the more into the distant past we're looking. And that's just simply because light has a finite speed and it takes time for light to reach us. So for example, the light from the sun, it takes 8 minutes to reach us. So if the sun were to magically turn off, we wouldn't find out about it for 8 whole minutes. Whereas the nearest star to us is about 3 light years away. That's the closest star. It still takes light 3 years to reach us. So when we're observing the system, we're actually observing as it looked like 3 years ago. The planets I was studying, most of them are about a few hundreds of light years away. So I'm effectively looking at things that have already happened hundreds of years ago, which blows my mind. So if we're looking for signals or detections, you're absolutely correct. That's stuff that's already happened in the past, simply because that information hasn't reached us yet. That being said, there are some stars that are as old as the universe and as our galaxy. The sun and the earth are sort of middle-aged comparatively to the rest of the universe. So there could be potentially a civilization that formed on a planet around one of these older stars, and it's billions, if not billions, of years older than our own. And that could be really cool to think about. There might be this very technologically advanced civilization. Or maybe they all got mad at each other and blew themselves up. Who knows? That's what makes the field so interesting. Hopefully it's not as depressing as the second option, though.
Okay, so we'll go for the last question here. And so Marcos says, will we find an Earth-like planet before we destroy the Earth? And my add-on to that is, if we do find one, what do you think that'll do as far as our attitudes and perspective about life here on Earth?
Yeah, I really hope so, Marcus. That would be great to find an Earth-like planet before we destroy the Earth. I'm trying to be optimistic here on this random Thursday night, drinking my soda water. But ask me again after I've had a beer, and that might change as well. But yeah, I really do hope so. I've always been interested in sci-fi person myself, and the question of are we alone in the universe is really one of those fundamental questions that's really going to change our entire history. Up until now, it's only been us on this one planet. And when we discover life, hopefully in the next decade or two, it could be that soon, which is incredible. That is going to just completely shift our perspective on everything and anything. And it's just going to completely change our history. So it's going to be incredible to live through. It's kind of interesting to live through COVID times and the pandemic and all the history that we've been through the last few years. And hopefully this will be something good that we can look forward to happening in the next few decades.
All right. Well, thank you so much. That's all for tonight. Thank you, Rob, for joining us this evening. And thank you, everyone, for tuning in. Join us for our next webinar on Monday, November 22, when Erica Blumenfeld from NASA's Johnson Space Center will share.
All right. Well, I don't know about you, but I kind of want to go try to find exoplanets with my telescope at home now. So that's something cool to think about. It's kind of funny to hear them talk about the Webb in future tense. We are lucky to live in the time where it is actually already flying. Well, so after this meeting, as we usually do, anybody wants to, are free to meet up at the Louis, which is actually just down the street from here. And I'm probably going to be there for like maybe 5 minutes before I have to go back to work. But it's a great place to eat if you haven't been there already. But before we do that, there's one more little cool thing we want to show you guys. So if you were at the last members night, you may have heard or seen the drone flying around, which was one of the coolest things I've seen, not at night, out there in a long time. And so Adam Koloff and Brian Wattenberger put together a video of a flyover of our observing field during a guest night. So let's see what that looks like. I haven't seen this yet, so I'm kind of excited. By the way, if you don't have one of these, they are the coolest toys ever, called the DJI Mavic Pro. Mavic 2 Pro, I'd say. That's pretty cool. We need our own TV commercial. That should be it. Well, other than that, does anybody have any club business they want to bring up before we conclude? All right, so I guess I declare this meeting adjourned. If anybody's going to Louis, I might see you there for a few minutes.